Step 1, define your targets. Step 3, analyze the results. Step 4 to 8, refine and achieve.
Create a 10 minutes video for YouTube about 8 steps to turn raw data into proven targets. Welcome to the world of geochemical data analysis. Think of this as your personal roadmap for turning a messy pile of laboratory numbers into high confidence geological insights. Whether you're looking for the next billion-dollar copper deposit, assessing environmental impacts, or just trying to survive your master's thesis, a structured workflow is your best friend. It is the difference between a defensible drill target and just poking holes in the ground based on a gut feeling. Geochemical analysis isn't just about looking at a spreadsheet and circling the high numbers. It is a journey that starts with building a foundation of trust in your data and ends with a map that tells a story. Along the way, we have to deal with unit conversions, weird statistical traps, and the fact that nature rarely plays fair. Let's dive into the 8-phase workflow that will turn you into a geochemical detective. Phase 1, the foundation. Building trust with QA/QC. Before you can even think about making a map, you have to ask yourself a very uncomfortable question. Is this data actually real? This is where quality assurance and quality control, or QA/QC, come into play. It is easily the most critical part of the process, yet it is often the first thing people skip because they are excited to see the results. Don't be that geologist. Think of quality assurance as being proactive. It involves all the systems you set up before you even take a sample, standardized protocols, training your team, and choosing a laboratory that doesn't just use a rusty microwave for digestion. Quality control is the reactive side. It's the set of checks you perform once the results come back to see if anything went sideways. You need a toolkit of control samples to do this right. First up are field duplicates. You take 2 samples from the exact same spot and label them differently. If the results come back wildly different, you either have a very nuggety deposit or your sampling technique is as consistent as a toddler with a crayon. Next are field blanks, pure silica sand or something you know is clean. If the lab finds gold in your blank, you've got a contamination problem somewhere between the bag and the beaker. Then we have certified reference materials, or CRMs. These are the gold standards, literally. You know exactly what's in them, and you submit them blind to the lab. If the lab says your 100 ppb standard is actually 50 pp, you have a systematic bias. We also look at laboratory duplicates and method blanks to see what's happening inside the lab's walls. Trust but verify is the name of the game here. Phase 2, data prep, cleaning the mess. So your QA/QC passed and you're feeling good. Now you have to deal with the messy reality of laboratory spreadsheets. Labs love to report data in a mix of units. You'll have major elements in percentages, trace elements in parts per million, and the really exciting stuff in parts per billion. Trying to do statistics on a data set with mixed units is like trying to calculate your gas mileage using liters per furlong. The first step here is unit consistency. Pick a unit and stick to it. Most pros prefer converting everything to parts per billion, ppb. It keeps the decimals away and makes the trace element numbers look a lot less intimidating. While you're at it, organize your master data set into a single source of truth. Samples go in rows, variables go in columns. This is the bedrock of your analysis. Now, let's talk about the below detection limit trap, or BDL. Instruments aren't magic. They have a sensitivity floor. When a result comes back as 5, it doesn't mean there is 0 gold. It just means the machine couldn't see it. Never ever set these values to 0. Doing so will crush your statistical variance and lie to your multivariate models. Common practice is to replace BDL values with half the detection limit or the detection limit divided by the square root of 2. It's easy, but it can introduce bias. If you want to be really fancy, you can use statistical imputation, which uses the relationships between other elements in the sample to guess the missing value. Just remember to always keep a copy of your original raw data. Once you start changing numbers, there's no going back if you didn't save a backup. Phase 3, the language of chemistry, molar conversions. Here is where we get a bit more scientific. Geology doesn't happen gram by gram, it happens atom by atom. Mineral formulas are stoichiometric, meaning they are built on specific ratios of atoms. If you are looking at the alteration of plagioclase to cerussite, you are witnessing a chemical reaction where potassium atoms replace sodium atoms. The problem is that a potassium atom weighs about 70% more than a sodium atom. If you only look at weight percentages or ppm, your data is lying to you. It will look like you've gained a massive amount of mass when in reality it was a simple one-for-one trade of atoms. To see the true geological process, you have to convert your mass units into moles. The math isn't scary. You just divide your concentration by the element's atomic mass. This simple step allows you to link your data trends directly to balanced chemical equations. It turns your data from a list of weights into a story about minerals. When you use molar element ratios, you can track exactly how much a mineral has been added or removed from a rock. This is the secret weapon for mapping out hydrothermal alteration zones. Phase 4, normalization. Finding the signal in the noise. Is 100 ppm of copper a significant find? If you're in a basalt, that's just a Tuesday. If you're in a quartz sandstone, you might have just found an anomaly. Context is everything. Normalization is the process of providing that context so you can distinguish a real mineralization signal from the background noise of the Earth's crust. The most basic method is Clark normalization. You divide your sample's concentration by the average abundance of that element in the Earth's crust, the Clark value. This gives you an enrichment factor. If your number is around 1, your rock is boringly average. If it's way above 1, you have an anomaly worth investigating. But nature has another trick up its sleeve. Iron and manganese oxides. In weathered environments, these minerals act like giant chemical sponges. They scavenge and concentrate trace metals like copper, lead, and zinc. This can create false anomalies that look amazing on a map but lead to a dry drill hole. To beat this, we normalize by iron or manganese. If your copper to iron ratio is still high, the anomaly is likely real. If it drops, you probably just found a very metallic, rusty rock. Phase 5, erosional level. Where are you in the system? This is the million-dollar question for exploration geologists. Every mineralized system has a top, a middle, and a bottom. The top is often barren, the middle is the rich ore zone, and the bottom, the roots, is where things start to peter out, because chemical elements precipitate at different temperatures and pressures. They create a predictable vertical zoning pattern. Think of it like a giant underground skyscraper. The elements Mo and W like to hang out in the hot basement. Su and Au are on the middle floors. PB, Zine, and Ag are usually way up in the penthouse. By looking at the relationships between these elements in your samples, you can figure out which floor you are currently standing on. We do this using correlation analysis and ordered series. We rank the indicator elements from highest to lowest concentration if your samples are dominated by lead and zinc. You might be looking at the super-ore halo on the top of the system. This means the prize might still be hidden deep beneath your feet. If you find the sub-ore roots, you might be too late. The good stuff has already eroded away and is currently a part of someone's beach house. Phase 6, the closure problem. Compositional Data Analysis, CoDA. Now, we need to talk about a math problem that keeps statisticians up at night, the closure problem. Geochemical data is compositional. This means all the parts have to add up to a whole, usually 100% or a million ppm. This constant sum constraint is a massive headache for standard statistics. Imagine you have a rock made of 50% mineral A and 50% mineral B. If a geological event adds more of mineral A, its percentage goes up. But because the total must always be 100%, the percentage of mineral B must go down, even if the actual amount of mineral B hasn't changed at all. This creates spurious correlations, negative relationships that don't actually exist in nature. If you run standard statistics on raw data, you are likely looking at mathematical artifacts rather than geological truths. The solution is compositional data analysis, or CoDA. We use log ratio transformations to move the data out of this closed space and into a space where the math actually works. The gold standard is the isometric log ratio, or ILR. It's a bit complex to interpret, but it's mathematically rigorous. The centered log ratio, or CLR, is also very popular because it treats all elements equally. By transforming your data first, your correlations become valid and your maps become much more reliable. You're no longer fighting the math, you're using it to see through the noise. Phase 7, statistic, reducing the chaos. Modern geochemical surveys often involve 40 or 50 different elements. Your brain cannot visualize a 50-dimensional graph. This is where multivariate statistics come in to save the day. The most powerful tool in your shed is principal component analysis, or PCA. PCA is like a high-tech trash compactor for data. It takes all those variables and compresses them into a few principal components that capture the most important variations in your data set. Instead of looking at 50 maps, you might only need to look at 3. The first component might represent the primary rock type, while the second might perfectly outline your alteration zone. We visualize this using a biplot, a 2D graph that shows both how the samples group together and which elements are driving those groups. But remember the golden rule: PCA must be performed on log ratio transformed data. If you don't, you're just compressing your mathematical artifacts into a prettier shape. We also use Hierarchical Cluster Analysis, HCA, to group samples by similarity. It creates a dendrogram, which looks like a family tree for your rocks. It's an unsupervised learning technique that lets the data speak for itself. It can reveal hidden groups that correspond to different lithologies or mineralization events that you might have missed just by looking at the raw numbers. Phase 8, visualization, bringing it all together. The final step is the synthesis. All your QA/QC, Molar conversions, normalizations, and stats culminate in the geochemical map. This is your primary tool for communicating your findings to stakeholders and deciding where to put the drill rig. But even here, there are better and worse ways to do it. One of the most robust methods is the quartile method. Instead of using arbitrary thresholds, you divide your data into 4 equal groups. The bottom 25%, background, the middle 2 groups, high background, and the top 25%, anomalous. Because this is non-parametric, it doesn't care if your data is skewed or has hurricane values, those extreme outliers that mess up standard averages. When you map these quartiles, you get what we call Quantic geochemical maps. They represent intensity in discrete population-based steps. This reduces noise and makes it very easy to compare different elements on the same scale. You can overlay these maps with your geological and structural data to find these sweet spots. High priority targets are defined where multiple quantic anomalies overlap across different indicator elements. By following this systematic workflow, you've gone from a pile of questionable lab numbers to a set of defensible, scientifically sound drill targets. You've accounted for contamination, the laws of chemistry, the traps of mathematics, and the spatial reality of the Earth. Geochemical data analysis is as much an art as it is a science. It requires a skeptical mind, a bit of mathematical patience, and a lot of geological intuition. But when you follow the steps, QA, QC, data prep, molar conversion, normalization, zoning, CoDA, and multivariate stats, the results are worth it. You become a dirt detective, uncovering the hidden stories of the Earth's crust, one sample at a time. If you are interested in these subjects, please subscribe, hit the like button, leave a comment from where are you visiting, and share this channel with your friends. Until next time, keep exploring.
Welcome to my channel, where you'll find over 2,000 videos on geology, geochemistry, AI, and many other subjects. If you like what you see, help us grow by subscribing, liking, and sharing this channel.
I think these videos are brilliant, and I'm sure you will like them too. Please like, comment, and subscribe, and don't forget to click the notification bell.